Hi, welcome back to the Physics Podcasts. In this episode, which I've entitled Measurement, Mathematics and Physics, I'm going to talk about some very simple measurements you can make to look at some quite sophisticated analysis of some physics concepts. Also, I'm going to have a look at some myths associated with measurement and the history of it throughout physics. First of all, I'm going to have a look at some work that Galileo did in the town of Pisa. Now, when I was in the town of Pisa, I asked some of the locals why it was that the tower leaned over. I was told, and I don't know if this is true, that the locals would go to the tavern, come home with quite a bit of alcohol in them, relieve themselves at the back of the tower, making the land on one side soggy, and therefore the tower leaned over. I don't know that I believe that, and in fact I don't know that I believe the story that Galileo dropped objects from the tower to determine the acceleration due to gravity. I've seen in his laboratory and I've seen the equipment he used. I will talk about that later on in this episode. But the conventional wisdom was that he would drop an object from the tower, it would fall straight down, and he measured how long it took to travel each section of the journey. So in the first unit of time, it was found that the object fell by 1 unit. The second unit of time, it was found that the object fell 3 units of distance. And in the third unit of time, it was found that the object fell 5 units of distance. Now, I remember when I first saw that just really amazed me that the universe operated by mathematics. Why should it be odd numbers that these distances relate to time? And then my mind really got quite blown away when I realised that these odd numbers, and Galileo called this the law of odds when he looked at objects falling, but he also noticed that when an object fell in the first unit of time, yes, it did fall 1 unit of distance, which is equivalent to 1 squared unit of distance. In 2 units of time, it fell 2 squared, or 4 units in total, the 1 and 3 units of distance. And in the third unit of time, it fell 9 units of distance, which is 3 squared units. And again, mathematics describes our universe, or in fact, our universe is mathematics. So he realised there's a relationship between the vertical displacement and the square of the time that it has travelled. He saw that S was proportional to t squared, and that eventually became the equation which you're familiar with, which is S equals ut plus half at squared. Again, we will always find that the universe can be explained by mathematics. Now, Galileo was a great measurer and a great experimenter. He did many experiments, but as I said, I don't think he found the acceleration due to gravity by dropping an object out of the Tower of Pisa. What he used was an inclined plane, and he set the ball to roll down the inclined plane. Now, you've got to remember, back in his day, they didn't have digital watches or very accurate timing devices, so he came up with a great idea as to how to measure the time. He placed notches along his inclined plane at various distances, such that as the ball fell, the noise it made was constant. Very, very clever experimenter. He did, however, use the Tower of Pisa for one very famous experiment, that is dropping objects of different masses. And he dropped objects of different masses and determined that they fell at the same rate. Again, conventional wisdom at the time, from Aristotle right through to Galileo, was that the heavier object would fall faster than the lighter one, but nowadays I'm hoping you know that all objects will accelerate at the same rate in the Earth's gravitational field. So very simple experiments he's done, which has changed the way that all humanity thinks about the world around them. And you can do simple experiments as well. We can perform really simple experiments that will demonstrate how mathematical the world is around us. Now, in class we had a very simple little pop gun here, and I challenged the students to determine a path that it would follow by placing rings and firing the object through. We measured the horizontal distances and vertical displacements. We plotted the data put the data into our calculators and plotted a curve which turned out to be a parabola, which verified the theory. Other experiments that we've performed are very simple ones looking at circular motion. The students will get a rubber stopper on the end of a string, whirl it round their head with masses at the end of the string pulling down, providing a tension in the string. Now, when they do that sort of an experiment, there are some very, very simple measurements that can be made, but as I said, you can do some quite sophisticated work with those measurements. So again, you can see there's slotted masses hanging down below the boy's elbow, the rubber stopper is spinning around his head. What we can do is we can measure the radius that the stopper, the circle that the stopper is following by measuring the length of the string. We can measure the mass of the slotted masses and therefore the weight force that it's pulling down. Now that weight force will provide a tension all the way along the string, which means it's going to be providing a centripetal force for the rubber stopper. We can plot lots of that information into a number of tables, and you can either use spreadsheets or calculators to, as I said, do some very sophisticated analysis of the data.